Hi, welcome to the tutorial on energy and more specifically on work and power, kinetic energy and potential energy, and types of energy, forms of energy will be covered on a different tutorial. And a quick side note, your notes, if you've downloaded the Cornell notes that go along with energy, more specifically work and power, the tutorial follows along in my own way on the tutorial, so it might not exactly match your Cornell notes, but you should be able to get most of what's needed in your Cornell notes to be able to complete most of it from the tutorial. So we use energy a lot in our everyday language, but what is energy? Well, it turns out that energy can be defined actually with another vocabulary word, work. Energy is the ability to do work. Alright, so having defined work, or energy rather, having defined energy, we need to define what work is. Well, work is basically a force that causes movement in the direction of that force. Now, the formula for work is basically, so off of here I'll just go formula. So the formula is force times distance. So the force you move something and the distance you move it. Now, units we measure force in, of course, would be newtons. So we would use a newton to measure force, like on a spring scale. Distance unit would be meters, for example. So when I take the force and I multiply it times the distance, I get this funky unit called a newton meter. And scientists don't like funky units like that, so we took and rearranged the name of a newton meter and decided a newton meter would be called a joule. So the unit for work and also a unit for energy is a joule. Alright, now I'm going to try to give you a better example of exactly what work is and how we'd calculate work in the following scenario. Alright, now I'm going to try to give you a little better example of exactly how we calculate work. So I need a tomato. Found one. I'm going to temporarily get rid of this newton meter scale. And let's say I apply a force on the tomato. So I apply a force on the tomato and the tomato moves. Okay, did I do work? Well, by the very definition of work, I did work. I applied a force and the tomato moved in that direction. So work was done. Well, how much work was done? Well, if you look at the formula for work, work is equal to force times distance. Well, very easy for me to see. If I move this from here to here, I moved it a meter. So that takes care of my distance, but how much force was used? Well, there's an easy way to figure that out. We just bring a Newton scale in here. Let's say I pull it, the tomato, a single meter. I can't pull them at the same time on here, so pretend the scale actually pulled that. Pull it 1 meter, and on the Newton scale, let's just pretend it actually said 1 Newton. So let's just use the formula to solve this problem to figure out how much work was done. So a force of 1 Newton was applied over a distance of 1 meter. Well, 1 times 1 is 1. A Newton times a meter we could rewrite as Newton times meter. And if you go back to the previous slide or so, you'll notice that we said, well, we're not going to use Newton meters for most things. We're going to rewrite that as a joule. So, if you applied a force of a Newton over a distance of a meter, you basically do a joule of work. Well, what happens then if I apply the force? Let's start back. Oh, oops. Actually, let's shrink that stuff up here. See if I can get that to shrink. Get rid of that, and I'll give you another example. So let's take our tomato back to the beginning. Let's say I pull it this time a distance of 3 meters. But let's say that tomato, well, let's go back in one more time here. Let's say the tomato grew first. Whoa, there's our oversized tomato. And now when I pull it with a Newton meter, it says 2 newtons, and I pull it a distance of 3 meters. So now we can use our equation here. Work is equal to a force of 2 newtons pulled a distance of 3 meters, which is equal to a total of 6 Newton meters, but we would rewrite that, Newton meters, but we would rewrite that as 6 joules. So that's 6 joules of work done. Alright, well that takes us pretty good through the work. So what in the world is power? Well, power is basically how fast the work gets done. So it's basically the speed, or how fast we do the work. And all you need, in addition to knowing how much work was done, is you need to know the time it took to do that. And usually we'd measure that in seconds. So in my previous example, we had an tomato being pulled, and it took 6 joules to pull that tomato. So 6 joules of work was done. Maybe I'm getting ahead of myself. So power, let's talk about the formula first. So what's the formula for power? Power is basically equal to work divided by time in seconds. And you could also write it this way, because work is equal to force times distance. If you weren't already given the work, you could calculate the work by taking the force times the distance, dividing it by the time. You could use either of those equations. So it's work divided by time, or force times distance if I give you a force and distance divided by time. So for example, in the previous tomato example, there was a total of 6 joules of work done. But it really didn't matter how fast or slow the tomato was pulled. Let's say I pull the tomato and it takes me only 2 seconds to pull the tomato. Right? It takes me 2 seconds to do that. That's equal to 3 joules divided by seconds, or joules divided by seconds. 3 joules of work done every second, basically. Well, again, scientists don't like units of joules per second, so what we do is we change the unit to something you've probably heard of, a watt. So 3 watts of work. So if I pull that tomato, and it took me 6 joules of energy or work to do that, and it took me 2 seconds, I basically produced 3 watts of power. So I could light a 3-watt light bulb by doing that much work. Now, what if I did the work a little faster? What if I, instead of 2 seconds, let's just say I did the work in 1 second. So 6 joules in 1 second, so it took me less time, would equal 6 joules per second, which is basically equal to 6 watts then. So by doing the work faster, that says watts, by doing the work faster, I basically produce more power. So here I use a different color. Here I did the work faster, and right here I did the work slower, and I produced more power. So on your Cornell notes, you probably have boxes where you're supposed to show your work by breaking out the formula. I didn't show it that way in here, but we've been doing that quite a while in class now. So I think I've covered the basics on work and power. The units for work are joules, the units for power are watts, and hopefully that will help you with your Cornell notes.